In this video, we'll look at Format4, which is the final format string challenge in exploit exercises Protostar. So this challenge looks at one method of redirecting execution in a process. So if we look at the source code, we can see that in the main function, we just call vuln. Vuln doesn't return normally. It calls exit with argument 1. And we have a buffer of size 512. We call fgets from standard in into the buffer, and then we call printf on the buffer. We also have a function here that's never really explicitly called, but it shows code execution redirected, and you win. So this is presumably what we want to call in our code. Okay, so after we kind of look through this, we can see that what the vulnerability, because this is obviously a format challenge, is going to be in this format string print with a user-defined format string. So again, Wikipedia provides a wonderful resource for learning about format strings, and especially what kind of parameters we can use to inside of a format string and what they symbolize. So for example, if we use a %HH specifier for the length field, this will cause printf to look at the argument as if it were a character. So this will allow us, in combination with the %in specifier, to write to a single byte without overriding anything beyond the byte. Similarly, we can do h to specify a word argument, and an L to specify a long size argument, which is typically going to be a 64-bit 64-bit number in memory. So even down here in the Wikipedia page, we can see that there's a link to uncontrolled format string, of course, and this is a software vulnerability with the printf function in the C family of languages that we've looked at before. Okay, so in this code, what can we really do? So here's the disassembly of the binary, and this will be useful for us because it will contain the addresses that we'll need to use. So in this main function, we can see obviously there's a call to vuln. Vuln is also a straightforward function. We have fgets with a local buffer here located 512 or 520 bytes below the base pointer of this function. We read in 512 bytes, and from this descriptor, which is the standard in handle here. And then we call printf on this exact string, which is this is the vulnerability, and then we call exit argument 1. We would like to get to this point here in hello. So if we can just look at this vulnerability here, we can see that the only thing that really happens after this printf is a call to exit. There's no return. This function doesn't return normally. There's just a call to exit. But exit is actually a imported library function, and its address is located in the global offset table here at address 8049724. So what happens in the call to exit is we really just get a jump to whatever address is stored in this memory location. Now, the thing about this memory location is that it's both readable and writable. Of course, it has to be, right? This is a dynamically linked binary, so obviously this address has to be written to whenever the program is loaded. And this, of course, happens in the libc start main. So what we can do is take advantage of this fact and kind of overwrite this address here with the address of the function that we want to call, which is hello. And of course, this can be really any function. In a real scenario, you will be able to see this. You can call any function that basically is in the text section just by changing the address of the library function. And we'll see this later on in some more practical exploits. So now that we have our attack strategy, we can kind of formulate what our format attack string will be. So of course, the first thing we want to do is find the offset of our format string relative to this printf the stack as printf sees it. So the way to do this is just to run the binary. So this is format4, and what we want to do is just supply some argument like this multiple times like this, and then kind of just see where our input starts to show up. So as you can see, the first argument is hex 200, then we have some B7FD. This is presumably a stack address, or at least it looks like an address on the stack. So does this one also. But starting here, we can see this is in big endian, so we really should start on the right-hand side. We get a 25, which 25 is the character equivalent of this percent sign. And similarly, 30 is the character equivalent of the 0, and so on. 38 is the 8, and 78 is the X symbol here. 7C turns out to be this vertical bar that I'm using to kind of delineate the different words in memory. So, so we can see from this immediately that our string is offset at a nice location. This is the first ordinal argument for printf. This is the second, this is the third, so we really start on the fourth one. And kind of to verify this, or to show this, we can kind of do something like ABCD, and then we're going to do the fourth argument from the stack and display it here. So of course we get the print of the ABCD first, because this is just part of the string literal, but after this we can see that we get a 41, 42, 43, 44, which is exactly ABCD in hexadecimal, and this is exactly what we expect. Okay, so now that we have the offset, we can kind of we know that we're going to put our addresses that we want to write to first, and then reference them with this %4 and $, and then we're going to use the %n to actually write to these addresses. So how should we write to these addresses? Well, there are a couple of options that we have. The first is we could just write it as a single word, but if we see the address of hello is quite large, it is 080484B4. And if we put that into our calculator, we can see that's more than 134 million. So obviously, we should not expect this to work because there should be some buffering issues actually with the standard, and we should not be able to input this many, or at least display this many characters with printf. So while this would have been nice, we can just do it all in one go. This probably won't work. Another option that we can do is to use, as we saw earlier, we can use word writes or short writes. So what this, we use the H length field, length specifier, to kind of show that this will be a short, which is going to be 2 bytes. And again, that might work, and actually that probably would work in this case, because we would need to write up to 84B4. As you can see, that's about 34,000, which is certainly much less than 150 million. But an even better approach would just be to write single bytes, which I think I like the best, which is simply we just give it the address of a single byte, and it will write the number of characters written so far, mod 256, of course, because it is a character. So to do this, what we do is we first notice that in our payload, let me go ahead and bring up Notepad. So we're going to have, of course, the addresses first. Because this is a word address or a double word address, we'll need to do 4 writes. So the first address we'll need to write to is going to be just the address here, which is 2497. So notice that when because this needs to be in little endian, because whenever printf sees this, it will see it as a little endian, and this is true for almost everything that you'll see. So this is the address of the lowest one, and we want to write to the byte that's just after this. So actually, if we can go to the hex view, yeah. So as you can see in this hex view, there's actually already a number here, but we're going to overwrite this starting with here, and then we're going to move to here and overwrite these 4 sequentially. So then we're going to do 05, then or 25, 26, 27. So you're keeping track. Every one of these is 4, and we have 4 of them. So essentially, you're going to have 16 bytes that are already written. So at this point in time, when we get to this point, n is equal to 16. So the number of characters written is equal to 16. Now we want to write first. We want to write before, and that's clearly significantly different from 16. So we need to fix that. We need to update from essentially 16, which is hex 10, to hex B4. And if you do the math, that comes out to an offset of hex A4. A4 is equivalent to A is 10, so 10 is 160, and we need 164. So we're going to go ahead and just do a percent sign here. Actually, do that. So we're going to do a percent sign to do a format string, and we're just going to use the first argument on the stack as our first argument, and we're going to do a percent, and we said 164, and we're going to format it according to it doesn't really matter what you put here. Again, this I use this %1 just to indicate we're going to use the first ordinal argument on the stack. You don't technically have to do this, but it's kind of nice to kind of see that your exploit is working, because if you always use this %1, you should always see the same number being formatted, just with different length fields. And of course, this will format it such that this 164, it will fit the number to the right side, or it will right align it, but everything else will just be blank spaces. If you wanted to fill it with zeros, you could prepend this with a 0. Okay, so now our counter, when we reach this point, will be correct, because we'll have displayed 164 additional characters, bringing our count to now B4. And now we can write to this the first address that we specified. So remember, the first address was at position 4, and we want to do a byte write, which is $HHN. So after we write B4, we want to get to 84. Now 84 obviously is less than B4, but remember, for a byte write, we are only concerned about the modulo 256 or hex 100. So really we want to take hex 184 and subtract B4. So if you do the math, hex 184 minus B4, the units digit will be 0, and then we want to carry, so that will be 18 or 24. 24 minus B, which is 11, will give us 13, which is hex D. 13 times 16 will give us 208. So that will be 208. So we want to perform, again, we're going to use this %1 just to specify that we're going to use the first argument, 208 for the hex, like this. Okay. So after we do that, our count will be 84, and we can perform our second write. So let's go ahead and do that. To do this, we're just going to specify %5. Remember, 4 points to this. 5 will be to this guy here. And we're going to do a byte write. Now we want to update from 84 to 04, which is, we can think about it, is 104 minus 84, which will give us hex 80, which is 100.8. And then we're going to do another write, so 5, 6. And then after this, we want to go from 04 to 08. Now, when we do when we want to display hexadecimal number for a word address, it won't let us just display 4. But it turns out if we actually specify the position, the ordinal, it will let us display however many digits we want to. In this case, let's just do, obviously, just 4. So this will actually work, even though if you do something like this, it will not work. It will actually display the full number. So, but this here will work. Okay, so after this, we now have hex 8 in our counter, and we just need to write that to the next location. So %7. All right, so this is our complete format string. we can go ahead and copy it into the program to check if it's running, or to check if it works. So we want to do echo, and we want to escape the bytes here. And it turns out if you do this, you don't actually need to escape the $sign or the %sign, which may cause issues otherwise. So we want to pipe this result into format4. And if we do that, first thing to notice, obviously, we redirected the code execution. We ran the hello function here that we were trying to in the first place. And the other thing is, if you just look around here, you can see just a bunch of these 200s lying around, and these are the first argument on the stack, the first ordinal argument on the stack that printf sees. And now that I think about it, actually, the last format here, person4x, probably worked because this argument was needed only 3 characters wide to display. Now, if it were larger than this, so for example, let's use, instead of that one, instead of the first argument, let's use the second argument to see what happens. If we do something like this, and then use send2 here instead, we get a seg fault because it actually tries to display the entire 8 digits. So in fact, the best way to actually approach this then, if you know that your if you know that the number needs to be a certain number less than 8, which is the size of that forward, instead of doing hex, you can use the same technique as what we saw earlier. You can display a half of a double word, or you can also just display %8hx, and this will actually give you 2 at most. So if you do that, you will see we still it will still work using the second argument because it only needs 2 digits to display. Now, if you only needed to write 1 character, obviously you can just put any character inside your format string, and that will just up your count by 1. Okay, so that was pretty much it. This was using format strings to redirect code execution, which is ultimately the goal that we have for these exploitation challenges. In the next few videos, I will actually be doing some more practical challenges that involve some vulnerabilities that are not so easy to see or not so easy to exploit. So I look forward to seeing you in the future videos.